Hello and welcome. This is the second video in chapter 22. In the first video, we had this series of experiments to just try and get a general picture of what electric charge is, where it comes from. Basically, the ideas were that objects can acquire electric charge via friction with other certain objects, right? And that charge kind of sticks to the spot where the friction occurred. And when it does that, it's able to attract or repel other objects that have been similarly charged with other rubbing forces. And it turns out that even electrically neutral objects that have not had any sort of contact, still acquire, or not acquire, but still feel an electric attraction to objects that have been charged, right? So opposites attract, neutral or like charges repel, but neutral is always attracted to any charge, either charge, plus or minus. And so that was the kind of one of the takeaway. In addition to the fact that materials are divided into broad categories of conductors and insulators. We'll talk about those in a little more detail in the video that we got, or in one of the simulations that we got in this video. So going back to electric charge, the idea is that because of one of those experiments, there are only two types of electric charge. And so we will formally define them as, and use this convention through the rest of the semester of positive and negative charge, right? It turns out that glass has the same charge that we associate with positive. Plastic has the same charge that we associate with negative. Those terms for positive and negative, right? They come from the fact that it's only one or the other, right? An object can also have a zero neutral charge as well. So the real number line really lends itself well to that, and there's no other type of charge an object can have. That's actually not possible at the nuclear level. The nuclear level, there's a different type of charge. It's not an electric charge. It's a different type of force called the strong nuclear force, and it's governed by what's called a color charge. That's not really necessary for this course, but it's kind of fun to consider that there are other types of quote-unquote charges out there. But we're just sticking with the typical positive-negative electric charge. And where does the charge come from? Well, what's the atomic source? Obviously, in this experiment, we're not going to do many of these quick check questions, but in this one right here, if we bring a charged object to a neutral object, right, you cannot conclude that both of them are charged. You can only conclude that one of them is charged, right? And they both could be, one is charged, either one is charged and one's neutral, or they're both oppositely charged. I'm going to skip this example real quick and move on to the main lecture here. So atoms and electricity, right? Where do we get the source of electric charge? It comes from the atom, right? And we're going to define our atom as our oversimplified picture of the atom as just a positively charged small nucleus surrounded by a negatively charged cloud of electrons, right? Obviously in the nucleus, there's protons and neutrons, and the atom as a whole is electrically neutral, but its constituents are not. The nucleus is positively charged, and it's very dense, and the electrons are negatively charged. They're extremely lightweight compared to the nucleus. In fact, the electron is the lightest object with a known constant mass, actually. It's kind of interesting. And to think about the scales here real quick, one scale that I've been thinking about, if the diameter of the atom is about 10 to the negative 10 meters, the diameter of the proton is about the nucleus is about 10 to the negative 15 meters, maybe a little bit bigger. If you take those numbers and kind of scale them out to everyday amounts, if you imagine the entire university campus in its a square mile block, between, maybe square half mile block between 17th and 21st Street, and then between Oliver and Hillside. If that entire area was empty space, then the nucleus would be at the very middle of that sort of rectangle, and it would only be about the size of a marble, right? Only about a centimeter compared to the almost square mile area of the entire campus. And that would all be empty space, actually, except for a very few number of electrons kind of floating around, whizzing around sort of the edges. So atoms are mainly empty space, and it's interesting to think of when you look around all these solid objects, right? They seem to be solid, but really it's just mostly empty space in between them. So that's one analogy. And since it's an important concept that you don't have in mass, actually, the concept of mass, concept of inertia, doesn't have this concept. But so since objects are made up of atoms, right? What is the charge of these electrons and these protons? And they happen to have the exact same amount of electric charge. It's equivalent. And so we define that quantity, we define an SI unit of electric charge called the coulomb. We can define it in terms of the, well, it's defined slightly different in terms of electric current, but for now, we just need to know that the electron and the proton have the same amount of electric charge, and that number is going to be 1.6, yeah, 1.6, sometimes 1.602. Looks like we're just going to do 1.6 times 10 to the negative 19 coulombs. So already we're going to hit the ground running with scientific notation in physics 2. In physics 1, we start off with very simple numbers, 2 meters per second, 5.0 seconds. We're already starting with heavy scientific notation, 1.6 times 10 to the negative 19 coulombs. And so, and obviously they're positive and they're negative and they're equal in magnitude. Their masses are much different. Obviously the proton is about 2,000 times bigger than the mass of the electron, okay? I mean, the concept of mass of a particle the concept of a particle kind of breaks down when you're talking about an atom, but there is still some semblance of a mass, and proton is much, much bigger. And that will come in handy, actually, when we're talking about magnets. Anyway. So since electrons and protons have a unit of charge that is inherent to their existence, right? The charge of the electron and the charge of the proton doesn't change from day to day. It just is a set number. It's like its mass. One would argue it's even a kind of like a quantum number. It's a little bit not quite the same as that, but because it stays constant. It's a fundamental input. And so, well, if objects are made up of atoms, then objects are made up of charges of electrons. All right, so if you think of what's the charge of an oxygen atom, right? An oxygen atom, a standard isotope of oxygen would be, it would have 16 protons, and, well, was that right? No, it has 8, sorry, it has 8 protons and 8 neutrons. So the charge of an oxygen nucleus is 8 times 1.6 10 to the negative 19 coulombs, right? But that's subtracted with the negative 8 times 1.6 10 to the negative 19 coulombs, and that cancels out. Okay, but if you're able to rip off some electrons, right, then the electric charge would be some multiple of it. Like say you ionize, let's say you take an oxygen atom and you ionize it, okay? So let's say there's only 7 electrons, right? Well then, what's the charge of it? The charge is just 8 positively charged protons, okay, minus 7 negatively charged electrons. And so it would be the result of a single positive charge of a single proton. Right? This idea just carries over. There's no new charge. The idea is that there's no new charge that comes out of the fact that there's more and more matter being clumped together. Right? There's not a charge that develops out of more objects being clumped together. kind of like there does with energy. Energy does kind of drift in and out when you bind objects together as you convert it to mass. But electric charge doesn't have that. So the electric charge of any object, whether it's an atom or whether it's a molecule or whether it's a balloon, it always has to be some integer multiple of the unit of electric charge. That's why this letter E is so important, 1.602 10 to the negative 19 coulombs. And this equation at the very top here, this number of protons minus number of electrons, it's general. Oftentimes we kind of abbreviate it and say that really what's going on is that there's always electrons. It's really just electrons that are taken from one thing to the other. It's very hard to take protons out and away from something, right? You're not going to ever do that with friction. You can do that with like some more advanced physics experiments, but not with everyday rubbing, not with everyday charging. So really the abbreviated version of this would just be Q equals N times this little e. And that N, or cap N, I think, is understood as the number of electrons that have been added or removed. Okay, so I think that if you use that abbreviation, you probably won't get into too much trouble. But this is a fundamental idea, the fact that electric charge is quantized, okay? Yeah, this is very different from mass. Mass doesn't behave in this way, actually. But electric charge is quantized. So the charge of every object is always some integer multiple of this 1.602 10 to the negative 19 coulombs, that specific number. So it's pretty fascinating. And so obviously we have here kind of this, the effective size of the atom changes as electrons are added or removed, right? Less electrons than the ion, positively charged ion looks kind of smaller, right? More electrons and the effective negatively charged ion looks bigger. That affects kind of the shape of molecules, right? If you think about like a hydrochloric acid or something, or think about some of these molecules with electrons removed in them, right? Like oxygen and H2O, oxygen atom, might look smaller because it's lost a couple of electrons to the hydrogen atoms. I mean, I know it's covalent, but anyway, so that's kind of interesting. This is an important part because this is realistically what's actually happening, right? If you look at the figure on the upper right here, you have a molecule, right? The molecule is effectively uncharged, and the friction from the rubbing causes these molecules to break, right? And energy is released, but also since the molecules are little molecular fragments, now these molecular fragments have the charges on them, right? And the charge of one is equal to the minus charge of the other, actually. And so this is what actually happens when objects get electrically charged, is that the outer kind of molecules break. Think about a balloon or of styrofoam. I mean, when you rub those things two together, right, you're really just breaking the molecular bonds. That friction is breaking molecular bonds between those two surfaces, and thus creating an electric charge at those spots because the bonds are now broken, right? And now each point of the balloon and the styrofoam now have sort of molecular fragments at that spot that are all kind of charged differently. So that's pretty interesting. An important picture to keep in mind moving forward when we talk about what's going on inside of a material, of a solid, for instance, would be this picture. So what's an insulator? So we're going to say inside an insulator, it's kind of boring, actually. Okay? We can model an insulating solid as a grid. The technical term is a lattice, but a grid of neutral atoms at each grid intersection point. And so to think about that, there's no electric charge roaming about anywhere in here. It's just a bunch of neutral atoms at these grid sites. So it's electrically neutral everywhere, right? And that makes the thing as a whole electrically neutral, because everything inside is electrically neutral and none of it is moving. So that's why when you rub an insulator, right, you might make a tiny piece of that insulator become electrically charged, but by and large, everything else just stays where it's at. Electric charge doesn't move very well in electrons themselves, don't move very well in an insulator. In a conductor, however, it's much different. And in a conductor, it's wild inside of a conducting atom. The atom, or sorry, the solid. The solid as a whole can be pretty neutral. The solid as a whole can be neutral. Say we got this, so let's say we got this little conducting atom of what looks like what would be 27 atoms, okay? And what's interesting, you need to kind of consider the condensed matter or the solid state physics behind it. But what's interesting is that if you take these 27 atoms on their own, they're all electrically neutral. Say you have 27 copper atoms, okay? You take 27 copper atoms, they're all separated by themselves, they're all neutral. Evidently, when they form a solid, evidently the energy of the solid is lowest if every single one of these atoms donates an electron to the overall solid. So it has this sort of phase shift, this phase transition where when it solidifies, so that the solid now is a grid of positively charged copper atoms surrounded by a gas of 27 electrons. So the 27 electrons are free to move about. Hopefully I moved to the right picture here. Yeah, this picture here is it's the neon gas simulation that I did in what would have been physics 1, where we imagine what an ideal gas looks like. But yeah, this picture, if you take this picture and overlay it onto that copper cube, that's pretty much what's going on for the electrons. So the electrons inside, to a very good approximation, act exactly like ideal gas molecules. Okay, so in a conductor, this is really important for when we start to go over how you get electricity to move in a conductor, right? You have a grid of positively charged ions, and that grid is existing with inside an ideal gas of the electrons. So the conductors, those are the ones that have all this freely moving charge, right? All of our electronic devices would never be able to function if we just, use the, oops, I wonder if you guys saw that, battery running low, of course. Saw those like outer charges on, the, sorry, I need to plug my PC in. Our modern electronic devices would never be able to function if we just used the kind of the outer, rubbing of, say, copper or balloons and styrofoams and plastic and glass and silk and wool and all these things. You can't run a computer. That's not nearly enough charge to run a computer. You'll see that modern laptop batteries have like 10,000 coulombs of electric charge stored in them. Okay, you need a ton of charge. And where's all the charge that we're using? It's in the conductors. Right? It's charge that's it's charge that has the ability to move in and out through the material or in between the material. And so we need to find the right way, much like water in a pipe, we need to find the right way to divert that water to the correct areas and so forth. So this is a really important idea about conductors. Conductors and insulators charge differently. For instance, if we're charging a conductor, I alluded to this earlier, you bring it into contact with the object, the charge will immediately go all the way to the outer surface. Any excess charge on a conductor will automatically go to the outer surface. And if you look at these pictures in series, what you'll see is that the charges will very quickly go. How do they know where to go, and how fast does it take for them to get there? It turns out that this rearrangement of charges is about at the speed of light, actually. They travel about nearly, the electrons don't travel at the speed of light, but the information about where the charge is distributed does travel nearly at the speed of light. And the speed of light's important because that's going to, well, not only will come up later, but that's how fast information travels for us. That's how you charge. That's how you charge a conductor. Discharging a conductor is the same thing, right? If you bring an uncharged conductor to a charged conductor, right? It drains almost instantaneously, and all the charge resides on the surface, right? So the same human body picture that we've got here. Now, what is charge polarization? Okay, the idea that so you have these little leaves down here. That little thing that looks like something from biology or chemistry, that's called an electroscope. Basically, it's a way to tell if an object is, positively charged or negatively charged. Those things at the bottom that are kind of bent outward, those are these little leaves. So what this does is if you bring it near it, what you'll see is if you bring the positive charge near this electroscope, right, the negative charge will be drawn towards it, the positive charge will be drawn away from it. So the thing, right, this little electroscope, while still being neutral, is now polarized. So objects can still be electrically neutral, but be polarized. Objects can be electrically charged and polarized, but they can be neutral and polarized. Polarized is different from being charged. And you see how this works in practice, because what's happening is that that rod, so this piece of metal, right, it's going to feel, you bring that rod towards it, the same charges as the rod are going to be pushed away. The different charges will be pushed towards, but because of the increased distance idea, the same charges as the rod are pushed away slightly less magnitude than the different charges are pulled towards it. And so you have a net force that points towards the rod. And if you switch the sign on the, so let's just zoom in, right? If you switch the sign on this thing, make it negative, then the same effect occurs. It's just the signs on the sides, on the edges of this thing are different, right? So if this rod was now negatively charged, you would have a larger positive charge on the top and the negative charge on the bottom. So charge polarization is the reason why neutral objects feel an attractive electrical force. And this happens, I'm going to skip ahead because it's kind of self-explanatory. This happens at the atomic level as well, right? So I bring a positively charged, atom or particle on the far left here, okay? The atom, which starts off having the nucleus effectively in the center, it kind of like morphs into this sort of egg-like shape. Now, it's definitely not to scale. It definitely, if you actually saw what's happening to the atom, this is definitely not to scale. It barely makes any noticeable change at all, but enough to make it so that it does feel an attractive force. So this positively charged dot here, right? It pulls the negatively charged electron cloud towards it. It pushes the positively charged nucleus away, and so now the atom itself feels an attractive force. So the neutral atom feels an attractive force to the negative or to the positively charged circle. right? If I switched this and made it negative, then once again, the proton or the nucleus would be drawn to it and the egg shape would switch, but you'd still have the positively charged or the attractive force. Okay, so charge polarization is an important thing because this is how neutral objects feel an attractive electric force to either positive or negative charges. Okay, and so yeah, this you see this effect occur at the sort of solid level, right? When you bring an electric charge to a solid, right, all the atoms in the solid undergo this sort of undergo this sort of polarization effect, and so the solid as a whole feels an attractive force to the dot, right? Newton's third law, the dot is attracted to the solid as well. So the last way that you can charge an object is via induction. Now, when it comes to induction, order matters. The way you charge the object is important, right? So when you charge it, so the first thing is you bring a charged rod to another conducting object. But the conducting object has to be connected to some much bigger object like a ground, like the earth or something, or human or some bigger object. Okay? So you bring the charged object to the neutral object, but the neutral object is connected to a bigger one, a bigger conductor, right? So when you do that, the neutral object will acquire a small charge, and the other bigger object to which it's connected will acquire the opposite charge. And then what do? You got to cut the cord. All right, you disconnect the neutral object to its big object, and then you remove the rod. Sorry about this little doohickey there. But that's how you charge an object by induction. You have to, so this is how you charge it without having any sort of contact with it, okay? So reviewing again, bring a charged object near a neutral conductor, but the neutral conductor is connected to a bigger conductor, okay? Disconnect the conductor and then remove the original charged object. If you do steps 2 and 3 in reverse, you won't get any effect. Like if you bring a charged object to the conductor, remove it, and then disconnect, then nothing happens. You have to bring the charged object to the neutral conductor, disconnect the neutral conductor to its bigger conducting object, and then remove it. That's the only way you're going to get the charge by induction. So in summary, there's a couple ways we can charge objects. We can charge them by contact. Right? We can charge them by rubbing. We can charge them by induction. And different methods of charging will work for different types of conductors or insulators, different types of electrical materials. So that ends our qualitative discussion of charge. What we'll be doing next is talking about kind of the quantitative rules of electric charge. We'll introduce the basic law, one of the most important basic laws of the course, which is Coulomb's law, and then do some practice with that. And then the chapter concludes with the concept of the electric field. So until then, as usual, thanks for your time, and we will see you back here for the next video. Take care.